explanation. I understood the explanation. You want to do the announcement?
Yeah. Shall we start? Yeah. Okay, everybody. So it's a pleasure to have Onkar here from Stanford, and he will tell us today something about black hole microstates.
All right. So thank you so much for the invitation. It's a real pleasure to be here. I wanted to tell you a little bit about a paper that came out last year and some work in progress with these people, Vijay Balasubramanian, David Bernstein, Aitor Ljukovic, Alex Miller, and Charles Abido. So the idea of this work is that we tend to think of black holes as, or black hole geometries as sort of universal description of a large class of underlying microstates. And well, so the typical picture or the thing that people have in mind is that there's some universal region in the black hole spacetime which is sort of you can think of as lying outside the horizon, which describes sort of universal physics that's accessible to simple operators or simple measurements in the field theory. Then there's some region behind the horizon which, depending on the specifics, can involve like some quantum completions of these geometry, some quantum fuzziness or something like that. I guess I should say that most of this talk is going to be based on AdS CFT, or the specific constructions that we talk about are based on AdS CFT. And at least in that context, the picture that one has in mind is that sort of the region, actually, more specifically, we are going to talk about sort of incipient black holes in AdS CFT. That is, black holes which have sort of very small horizons, so the horizons are very close to the singularity of the black hole. And in that case, the picture one has in mind is that the sort of region outside the horizon is sort of the universal part of the space-time which captures most of the classical information, and everything behind the horizon is some quantum fuzziness that cannot be described by geometry. And so this is the sort of picture we'll be revisiting in this talk, but from a slightly different perspective. In particular, we're going to revisit it from the perspective of phase space, and we sort of want to understand the phase space of excitations around this geometry. But we'll do this in a very concrete example of a specific black hole, which is dual to half-BPS states, or some very supersymmetric states in n equals 4 super Yang-Mills. And then, so we'll try to study the space of excitations around this geometry, both from a classical and from a field theory and from a gravitational perspective. And the idea will be that in doing the calculation in gravity or in supergravity, one encounters a somewhat surprising mode in the phase space, a sort of soft mode, which seems like it lives in the horizon of the black hole. And then the aim of the talk will be to try and construct the same excitation or the same soft mode from the CFT perspective, and explain its origin, therefore explain its origin microscopically. Okay. This is, most of this is just motivation, but similar soft modes have also appeared in discussions of black hole information in recent years, and so I guess part of the hope of these studies was to try and understand black hole entropy from this perspective, but we are not entirely there yet. But I think this is a nice example in which some of these ideas become clear. So that was mostly just motivation. Now before getting into the details, let me briefly review for you the two sides of the story that we are going to need, the CFT side and the gravity side. So from the CFT side, we are interested in half-BPS states, or the half-BPS sector of n equals 4 superangles. So the nice thing about this sector is that it's described essentially by a matrix model. So all of the states, all of the half-BPS states of n equals 4 superangles can be described in terms of the following matrix model. Okay, where X is an n by n matrix. You can think of it as one of the scalars which lies in the scalar, one of the 6 scalars in the n equals 4 superangles theory. So, but for my purposes, you can just think of X as an n by n matrix, and this capital DT is basically the time derivative, but it's a covariantized time derivative. So there's a gauge field in there, and in particular that gauge field is dynamical. So it sort of imposes the singlet constraint. Okay. But because this is just a theory of one matrix, you can reduce it to its eigenvalues. The fact that you can reduce it to its eigenvalues comes from the fact that there's a Gauss law corresponding to the gauge field in the picture. But nevertheless, you can reduce the theory to the n eigenvalues of this matrix X. Okay, so lambda I is the eigenvalues of X. Yes.
Why it's reduced to quantum mechanics? I mean, this, in general, I would have expected this to be a field theory.
It is, yeah. But so the half-BPS sector is essentially you can just look at the S wave. So say you put n equals 4 superangles on S3. Then for the half-BPS sector, you just look at the S wave of these fields. And that's, so basically that gets rid of all the spatial dependence in the field theory and you get a quantum mechanics.
And so these matrices are connected to the rank of the gauge group, right?
That's right.
Okay.
They're n by n, or SU n views. So the this n is not that same n. This, of course, is the n of supersymmetry. But yeah, the n that is appearing here is the rank of the gauge. All right. So so as you can see, the half-BPS sector of n equals 4 superangles is extremely simple. You can describe it by n-free harmonic oscillators. The only subtlety that you have to keep in mind is that in going from the matrix description to the eigenvalue description, there is a van der Waals determinant in the wave function that usually gets absorbed in the wave function. So what I'm saying is that in going from the measure over matrices, n by n matrices, to sort of the measure over eigenvalues, there is a determinant, which is usually called the van der Waals determinant. Something like that. There is this factor that comes in the change of measure. And what one does is, since you don't want to think about this measure, you basically absorb this inside your wave function. What that does for you is because this actually you absorb 1 power of this factor inside the wave function. What that does is it makes these fermions anti-symmetric. So anytime you exchange I with J, you get a minus sign. That basically comes from this measure factor. Okay. So long story short, you can describe the half-BPS sector of this model by n-free fermions. Okay. There are n fermions in the harmonic oscillator potential. Okay. So it's a very, very simple description. Good. So having said that, we can now describe the space of half-BPS states in the Yang-Mills theory. What is the ground state? Well, I have a bunch of fermions in the simple harmonic oscillator potential. So imagine you have the sort of energy levels of a simple harmonic oscillator. Okay, evenly spaced. The ground state will be, the crucial thing is that these are fermions. So the ground state just amounts to filling up the first n energy levels. Okay? The first n of them. This is because these are fermionic particles, so I can't put two in the same energy level. So I need to fill up the first n of the energy levels, and that's the ground state. This is the ground state. This is the same as the ground state of n equals 4, which is in AdS CFT, it's dual to classical just AdS spacetime. Okay. And so that's the ground state, but excited states in this sector are also extremely simple to describe.
So the only justification for you're saying that these are fermions or that the fermions or whatever?
Yeah. So in other words, you absorb one of these powers inside the HET, the other power inside the bra, and so the wave function becomes antisymmetric in the exchange of eigenvalues. That's the good. So that's any other questions? All right. So that's the ground state. Excited states are also very simple to describe. So the way you could construct excited states is you basically excite some of these formulas, right? So say I excite this guy here, somewhere here, by 3 or by 3 energy levels, and say I excite this guy by 3 or by 2. And so on, right? Basically, you get the picture. Excited states are just created by exciting these fermions out of the ground. Okay. There's a nice description of these states in terms of Young diagrams. The way it works is that depending on how, so you basically draw a Young diagram corresponding to the excitations. So for example, the one I drew here corresponds to that Young diagram. The way you go between them is that the number of boxes in the first row of the Young diagram corresponds to how excited the topmost fermion is. So here the topmost fermion was excited by 3 energy levels. So the top row of the Young diagram has 3 boxes. All right. The second fermion was excited by 2 energy levels. So there are 2 boxes here. Okay, and that's it. There are no more excitations. So in other words, there's a correspondence between excited states in the half-BPS sector and Young diagrams of this type.
Why do you have to preserve the order?
Why do I
Why
have
couldn't the second one have jumped to the other?
That's right, but so these fermions are basically identical because there is an SN symmetry in the action, right? So up to a minus sign, that's equivalent. Yeah. So that's why you can describe them in terms of Young diagrams. It doesn't matter what the order is. All right, very good. So that's a sort of, if you like, a convenient shorthand for describing these excited states in the super-Yang theory. But there's another nice way to describe these states. Maybe I should write.
Question. So these Young diagrams, are they like representations of some state? Or is it just like, you just take the exact?
They are representations. So I said that there's an SN symmetry in the Lagrangian, which sort of formulates these eigenvalues. So I think you can think of them in terms of representations of that SN. Yeah. So a somewhat more convenient way to think about these states is to do the following. So we can construct sort of second quantized operators. So I'm going to call them psi n and psi m dagger. So what psi n does, or psi n dagger does, for example, is that it creates a fermion in the energy level m of the simple harmonic oscillator. Okay, and psi n will correspondingly annihilate such a fermion. So these second quantized operators satisfy the usual algebra of creation and annihilation operators. So in terms of these creation and annihilation operators, you can define. Maybe it's easier to write it separately. Where I've defined a new operator here, psi of q, which in terms of those old creation and annihilation operators are basically the following. Okay, so these psi n, I told you, they create or annihilate operators in the n energy level of the harmonic oscillator. These fn's are basically just the wave functions of the harmonic oscillator in the n energy level. So these are the standard harmonic polynomials, the Gaussian multiply. So when you do the sum, roughly you should think of this operator psi of q as creating a fermion or destroying a fermion at the position q in the harmonic oscillator. If you think of q as the sort of configuration space variable of the harmonic oscillator. Okay. So now, in terms of these new operators psi of q, what this u is like it's essentially like this is analogous to the Wigner density. So in other words, it's an operator in two variables, q and p. This q and p you should think of as the phase space of the simple harmonic oscillator. And what this is measuring is it's sort of measuring some kind of probability distribution that a fermion sits at the position q and p in phase space. Okay? So this is called the Wigner density. It's not really a probability distribution. It's a quasi-probability distribution because it can go negative. But in sufficiently classical states, and I'll describe what I mean by classical in a second, but in sufficiently classical states, you can think of this u as being like a probability distribution. Okay, it tells you again the probability that there is a fermion at the position q and p in phase space. Okay, so for example, here's my phase space parameterized by q and p. Suppose I had a fermion or suppose I had a simple harmonic oscillator which was in an energy eigenstate. And if you try to calculate this u in this energy eigenstate, what you would find is that this object u sort of looks like a ring. At the location, at the radius, p squared plus q squared over 2 equals the energy. Okay? So if you have a fermion in an energy eigenstate with energy E, then this quasi-probability distribution U looks, in that state, it looks like sort of a ring of thickness h bar that's peaked, if you like, at that value of the energy, or at that value of the radius p squared plus q squared. Okay? And this thickness is h bar. Okay? So this is, in some sense, telling you that if a harmonic oscillator in that energy level is sort of peaked in this region of phase space, okay, which you should probably have expected. Okay, that I hope that's not a surprise. Very good. So if you have, so that was just one oscillator. But now, for example, in our context, our states are described by having n fermions. Okay, so for example, if I have the ground state, then what's going to happen is that you can think of this entire phase space as being tiled by these rings of different radii. If you have the first n of them filled up, you're going to have like the first n rings, if you like, you're filled up, right? All of these are going to be filled up and empty outside of that. Does that make sense? Good. So in phase space then, the picture for the ground state is that you have like a disk which is filled up to the energy level n times, or to the radius n times h bar. So the p squared plus q squared over 2 has to be n times h bar. The n comes because there are n fermions, h bar because each of these rings have thickness h bar. Okay? And now we can discuss what we mean by the classical limit. So if I send h bar to 0, then this will shrink. But at the same time, if n is large, then I can send n to infinity. Okay? So if I send n to infinity and h bar to 0, but with n times h bar fixed, then what's going to happen is that this disk is going to stay of finite size, but it's going to be like a filled disk of finite size, right? So this is what I mean by the classical limit, and we'll see in a moment that this. This is a description of the vacuum state.
But you forgot the important 1/2 here.
I haven't forgotten it. It's there. The radius is 2 times n. Is this the factor of half you're talking about?
No.
No.
Harmonic oscillator has H plus 1/2 H bar.
Yes, but that fits.
Do you care about it?
Yeah, I mean that. I think in the classical limit,
That's the limit
it
of
doesn't
energies,
really matter.
right?
That's
It's 1/2
right.
times h bar.
Yeah, and that's not scaling with
And
n.
I'm also not sure, I mean, he's looking at fermions, right? So you're thinking about those.
So the point is n times 1/2 plus H bar. So it's not vanish, it's close to infinity.
And normally it should vanish, right? Oh, you say so the energy
I mean,
level
this
of
is
the ground state.
one of the paradoxes of early days of QED. Yeah? Just people thought that there was infinity because it's 1/2. But anyway, just
Yeah, I mean, I think the point is that it's true that the quantum energy is that, but if you calculate this Wigner density for an energy eigenstate, I think it's still sort of peaked around. Yeah.
I thought these were fermions, so shouldn't those energies be different?
Which energies?
No?
Oh, so the energy levels, you mean?
Yeah.
So what the fermionic nature is it just goes into filling up these energy levels. The energies are the same because the potential is still that of the harmonic oscillator.
I see.
Yeah. So the energy levels are just fixed right now.
Okay.
And then the fermionic nature comes in and filling up these energy levels. All right, yeah, we're coming back to, yeah, that's a good question, but I think if you look at the Wigner density, then it's still sort of nice, and it doesn't see this half of h bar fraction, as far as I'm aware, but that's a good question. All right, so that's a description of the vacuum state. Excited states like these I was describing here, in this classical picture, what happens is that these excited states correspond to sort of wiggling of the boundary of this disk. Okay, so the vacuum state is like the disk, filled up disk, and if you excite states there, that sort of wiggles around this the boundary of the disk. Okay, so you can convince. I'm not going to show that here, but that's the picture. You can convince yourself that that's the case. Very good. So this is at least true for small excitations. For large excitations, you can sort of imagine that the disk splits off. There are portions of this disk that split off, and so on. There's topology theory. Those are large excitations, and we'll come back to that momentarily. All right. So that was the discussion in field theory. Now let me quickly tell you what the dual of this picture is in gravity. So in type 2b supergravity, the dual for all of these states was written down by Lin, Lunin, and Navasena. So these are called LLM geometries. So the metric, I should mention that the thing that I'm going to write down are solutions of 2b supergravity. Okay. So the metric looks like as follows. And there is also the four-form gauge field is also turned on. I probably don't, well, there's a four-form gauge field turned on. It's not super important what that looks like. But let's just look at the metric for the time being. That's super important. Let's see. So there are these various fields appearing here. The main thing that I want to draw your attention to is these three coordinates, is y, x1, and x2. All right. So all of these other functions like h and bi and g and so on, these are all functions of these three coordinates. Okay. This is mostly where all of the action is happening, in the y, x1, and x2 space. Okay. In addition, there are these two. So, okay, before that, I should tell you that this coordinate y is always greater than 0. So it's a positive coordinate. And x1 and x2 just live in R2. So they are just real values. Very good. Now, all these functions, as I said, h, g, and so on, are just functions of y, x1, and x2. In addition to that, there is, of course, time. But there are also these three spheres hanging around. So there are 2 3 spheres, so this is one 3 sphere, and there's another one which I've denoted with a tilde here. Okay. So there are these 2 3 spheres hanging around. That's 6 coordinates plus the y and x1 plus x2 is 9, and then there is time. Okay, so that's 10. Very good. And now, for this to be a solution, the various h, v, g, and so on, I have to tell you what they look like. Basically, what happens is that they are all just functions of a particular function, which I'm going to call z. So there is basically one function, z of these 3 coordinates, which essentially entirely determines all of the other functions. You can write all of these functions in terms of this one guy, and this one guy satisfies a very nice differential equation. So it essentially satisfies a Laplace-like differential equation in these coordinates y, x1, and x2. You should probably have expected this because the BPS nature of these geometries sort of imposes this linear equation of motion. And so we know exactly how to solve this, of course. The solution is very simple.
Actually, from BPS, I would have expected it to be first order.
Yeah, okay, that's a good point. But what I meant by that comment is that usually BPS solutions tend to have this property that you can superpose them. This is essentially what I meant by the fact that this is linear. This equation is linear in Z, so I can take multiple solutions of this equation and superpose them and get a new solution. This is the kind of thing that happens. So now I'm putting these vector signs on X, which just means that it's a vector, it's X1 and X2. Okay. So this is a solution of that differential equation. Note that there is this quantity Z0, which only depends on these X1 and X2. Okay. That's the boundary condition, right? So I told you that this Y has to be greater than 0. So I can solve this differential equation up to a boundary condition at Y equals 0, and this is that boundary condition. Okay, and it just depends on two coordinates, X1 and X2. So at this point, I've essentially told you what the metric is. All of these other functions can be written in terms of the Z, and I'm not going to give you the details on that. You can look up their paper. It's not super important. But what's important is that you can check that for this metric that we wrote down to be regular, this Z0 cannot be arbitrary. Okay, so what Lin, Lunin, and Nordesena showed was that this Z0 has to take on, it basically can take on only two values. Okay, it can either be plus half or minus half. Okay, that's the regularity of that metric in the limit that Y goes to 0 fixes these two conditions.
And it's constant with respect to the X.
Exactly. That's right. It's constant, it's at least locally constant. So you can have some regions where Z0 is half and other regions where it is minus half. But locally it has to be either plus half or minus half. The reason for this is that when Z0 is plus half, what happens is one of these three spheres shrinks smoothly to 0 and the other three spheres of finite size. When Z0 is minus half, the other three spheres shrinks smoothly to 0 as you go to Y goes in the limit that Y goes to 0, and the other three spheres stays of finite size. When at the boundaries of these regions, both these spheres shrink smoothly to 0, and the geometry is still regular. But any other value of Z0 leads to a singular solution, because in that case, the spheres don't shrink smoothly to 0, and then you encounter a that on the Y equals 0. Okay. So now this should probably remind you of the discussion we had in the CFT case, where we had this phase space of two coordinates, Q and P. And then there were some regions which were filled up and some other regions which were empty. Okay? Indeed, so you can show, so the correspondence between supergravity and the field theory description in this case is precisely that. So the correspondence is basically the following. So let me just write it here. So the correspondence is that what we called U, which was the space-phase density in the description, in the CFT description, as a function of Q and P, this is exactly 1/2 minus the boundary condition Z0 that we discussed over there. And there I call these coordinates X1 and X2, but just relabel them as zero. Yes?
Sorry, how do you make a connection between this?
I'm just telling you that this is the case. This was discovered by Lunin and Nordesena. So the one way to see that is for the ground state, for example. In the ground state, the phase space density, as I told you, is just a disk which is filled inside and empty outside. Right? You can take this prescription, translate it to Z0, and plug that Z0 into this metric and see what you get. And you get precisely AdS 5 times S5, which is the usual statement that the ground state corresponds to AdS 5 times S5. And similarly, you can check that for excited states in the half-BPS description, you can construct geometries or metrics here, and you can use like standard AdS CFT to compute correlation functions, for example, the stress tensor, one-point function, and so on. And you can match them exactly. Okay, so this was the correspondence between the two sides that was discovered by the very good. So, right, so this is, any other questions? So this is the correspondence, or this is how AdS CFT works in the half-BPS section. Okay, there are explicit constructions of CFT states and bulk geometries that we just discussed here, and we just discussed what their correspondence is. Okay, so much for that. Now I guess I should speed up a little bit. Yeah.
So typically holography, in the dictionary, like what people usually say that like there are finitely many, on the CFT side, there are finitely many primaries below a certain cutoff, and then you have like a density of primary goes up high above the cutoff.
That's usually for spin operators. Like there's a twist gap.
Right. Well, isn't that for scalar dimensions as well?
Not for scalar operators, because you can have Kalutza-Klein excitation, right?
But well, that's true.
They're not supermassive, right? Because the radius of the S5 is big.
Right.
So usually for spin operators, right? So the gap statement, people usually mean that there are no stringy excitations, which means that there are no higher spin operators. Those are extremely massive in the string theory side, which means that they're high dimension on the CFT side.
So what I was going with this is
LADS
is large.
Say that again?
Like in the last equation.
Yes.
LADS, which is large.
Yeah.
So that is implying that n is super big number.
Well, usually we say that LADS is large in string units. So here the statement is that you take n to be large, h bar to be 0, which means that you're sending the Planck length to 0.
Right.
But you're keeping LADS fixed. So in other words, here the statement is that LADS is being kept fixed in Planck units.
Right. And n is large.
N is large, right? And,
So, is there no issue like you have like a lot of operators in the ground state?
a lot of
Because
operators.
like you got this number 2n by the ground state, right? At the ground state you had n operators.
Well, it's not that there are n operators. Okay, so one thing you should keep in mind is that this is a gauged matrix model, right? So not every operator is physical. There are only like singlet excitations, like traces are allowed. They are the only physical excitations, for example. So they don't scale with n. Right. All right, good. So now that was just a review of the way AdS CFT works in the half-BPS sector. But what do we want to do with these? So the introduction involves black holes and microstates and so on. So the kind of states that we want to discuss in this correspondence so now I have my pictures drawn over here. So are states which look from the CFT point of view like this, okay? They are a large number of rings. So here I only do 4 rings. But imagine that you have a very large number of rings of this form in the phase space or in that x1, x2 plane that we discussed over there. Okay? Now imagine that these rings were each of h bar size. Okay? And there again the spacings are also h bar. So if you wanted to describe this with the Young diagram picture that I discussed before, that looks like a triangular Young diagram like this. But if this picture is not super helpful, then don't worry about it. If it's natural, that's great. The point is that these are highly excited states. Okay, so this is order n, and again this is order n. So these are highly excited states. But the important thing about these states, although they're completely well defined quantum mechanically, there is no classical limit. Okay? So if you try to send n to infinity and h bar to 0, the quantity u, or z0 if you like, is still highly oscillatory. because it's 0, 1, 0, 1, 0, 1, and so on. Right? It keeps oscillating very frequently. So there's no classical limit for these states. Okay? They're well-defined states in quantum mechanics, but they don't have a nice classical limit, which I can use to translate them into geometries in gravity. So then the question becomes, what is the geometric description, if at all there exists one, in gravity? Okay? So one thing that you might do is you might say, okay, this state corresponds to a highly oscillating phase space density in quantum mechanics, but maybe I can coarse grain it a little bit. Okay? It's highly oscillatory. So if I don't look at scales which are of order h bar, then what this picture will look like is it essentially, I'm drawing the coarse grain picture here now. It will look like a disk, which is not, it's not either white or black. In other words, it's not like filled or unfilled, but it's sort of gray. So if you imagine this as a collection of black and white rings, which it is, then the coarse grain picture here will look sort of gray. Okay? In equations, the quantity u that we had there will not be 0 or 1, it will be half inside here. Okay? So that's great. So now I have at least a prescription to work with. I take this state, I coarse grain it, I get a phase space density which is half inside some disk, and then I use my AdS CFT dictionary to construct a metric. Okay? If you do that, what happens is that you get a geometry which is singular in the y going to 0 limit. Okay, this is what is called a superstar geometry. It's essentially like a black hole, which has a singularity at some point. And you can think of the singularity as sort of the horizon having gone and collapsed onto the singularity. So it has no horizon. It does not have a finite size horizon. But you can think of it as a very tiny black hole, where the horizon is close to the singularity, if you like. Okay? So what this discussion is telling you is that there is a class of states in quantum mechanics which are entirely well defined, but their gravity description can have a singularity. Okay? So in some sense, this is hinting at some signature of how to resolve black hole singularities in AdS CFT. These are a class of quantum mechanically well-defined states, but the gravity description can involve some, to make gravity description precise, you have to do some coarse graining, and that introduces the singularity. Yeah?
This might be a silly question.
No, go ahead.
But initially you said the ground state looks circular, and if you have excited state, the shape might deform.
Yeah.
Right, so, but wouldn't only the excited states correspond to the black hole?
Yeah, so those are highly excited states.
But they still look circular.
They look circular, but a very large radius. So the radius is not the same. This radius is much different. But secondly, the important difference between this and that is that that disk was like density 1 inside and 0 outside. This is, in the microscopic description, the density is highly fluctuating. So if I just plot the density as a function of radius on this plane, this density is highly oscillating. It's doing that. If you coarse grain it, then it sort of looks like it's constant at half, not 1. Whereas the vacuum looks at, it's 1 and then 0 after some radius. Yeah, so you're right, these are extremely excited states. In fact, they have energy order n squared.
So according to your dictionary over there, if u is 1/2, then z will be vanished, yes?
Say that again?
According to your dictionary, if u is 1/2, then z is 0.
Yeah.
This is the superstar thing that?
Yeah. So you plug that in to this metric, you get some metric. That's the superstar metric. And it has a singularity.
Some metric means Schwarzschild, right?
No, it's not the Schwarzschild.
But you just said it's like to take the horizon and push it into 0. It should look like Schwarzschild everywhere outside.
Well, for example, asymptotically, it looks like AdS space.
Oh, like Schwarzschild in
AdS, yeah.
Yeah, right.
All right, good.
Do you have a picture of what's happening in the brain description?
In the what?
In the brain description. So previously you could trace everything that
Yeah.
the eigenvalues are the positions of the branes, if the matrices are diagonalizable and so on.
Yeah.
And so I imagine these are highly non-diagonalizable. Or what? What is happening?
No, these individual eigenvalues are like branes. And so what's happening is that these branes are sort of getting organized on the internal S5 in some highly non-trivial configuration. So there are like branes placed on the internal S5 in some way, and they're spinning on the S5. So they have large angular momentum, which is why these states are high energy. Yeah. So in this context, these branes are called giant gravitons. Good. Anyway, so that's the basic setup for these black holes. And what we want to do with these black holes is we want to study the sort of phase space of excitations around these black holes. So I have about 10 to 15 minutes left. I'm going to sort of give you the brief overview of our calculation. I'll try not to go through the details of the calculation because I have 15 minutes left, but you're welcome to ask me questions later. All right, so the kind of excitations that we want to study are the following. So I told you that in the space, these states look like gray disks. By gray, I mean that the density in here is half. Okay, it's not like 0 or 1, but it's half. Okay, so that's what I mean by gray disk. Now I can think about fluctuations where this grayness changes a little bit. So imagine that there are some fluctuations here where the grayscale changes. Okay, so this corresponds to some field delta U, which is a function of x1 and x2. Okay, and so that the total density is U0 plus this. So this is half, and then there are some grayscale fluctuations on top of that. So this delta U goes between minus half and plus. All right. So these are the kind of fluctuations. You can think of these as some kind of fluctuations around the black hole. I like to think about them as hydrodynamic fluctuations because first of all, this can be a long wavelength field, and if you plug this into the metric, you get some fluctuations which propagate out to asymptotic infinity. Okay, so these are some kind of hydrodynamic fluctuations with the black hole, analogous to those you find in fluid dynamics or in the fluid gravity correspondence. Okay, so what do we want to do with these fluctuations? We want to understand the phase space. Okay, so whenever you have some fluctuations, you can talk about sort of the phase space of these fluctuations, and that's what we want to understand. In other words, the question is, if I give you this mode in gravity, what is the conjugate momentum for this particular mode? Okay, hydrodynamic mode. So the way you do that is you calculate the symplectic form. So type 2b supergravity has a symplectic form. Okay, so very roughly that symplectic form looks like the following. So I'm not going to write out all the indices, but roughly the point is that there's a metric, its conjugate momentum is like the extrinsic curvature. So you pick some constant time slice. This is a 9-dimensional slice in 2b supergravity. And the fields which are turned on in this metric are in this particular solution are the metric and the four-form gauge field. They have a symplectic form, so you should think of this as basically dq at dp, where q is like the metric and k here is its conjugate momentum, which in gravity turns out to be the extrinsic curvature of the slice, and similarly for the four-form gauge field. Okay,
this is always true. Right?
Sorry,
isn't this always true?
This is always true. Yeah. So this is just a symplectic form for 2D supergravity. What you can do is you can take this metric and you can plug it in here, and you can then, so that generates for you a symplectic form on these excitations. Okay? Good. So I should mention that this calculation was done in the microstates. In other words, when U is 0 or 1, by Maus and Richkov. They have a very nice paper on this subject. But the main difference here is that we want to do it around this black hole. Okay? So we want to study the symplectic form for excitations of this black hole geometry. So yeah.
So isn't there a problem with the self-duality of the phi form? Because normally the story is that you cannot even write down an action for
That's
type
right.
2, right? And so, but you say you can write down a Lagrangian because then you can write down a symplectic form.
You can write down a symplectic form. I don't know whether you can, that comes from a Lagrangian or not. But there's a well-defined symplectic form that you can write. So this symplectic form was written down by Maus and Richkov. Yeah, maybe we can address this question a little bit later, but at least Maus and Richkov chose a particular symplectic form, which seems to make sense. And in the case of their calculation in the microstate, it agrees with the symplectic form of the half-BPS sector of n equals 4. So it seems like the form that they're using is a kosher symplectic form. But that, yeah, it's a good question how to relate it to the Lagrangian. Good. So I'll spare you the details of this calculation. The important thing is that when you go ahead with this calculation, you find an interesting result. What you find is that this entire integral reduces down to basically these two coordinates, x1 and x2, that we came across before. And the symplectic form reduces to something very simple. Okay, so this delta U is, of course, the same grayscale fluctuation, the fluctuation around the black hole. But you find that there is an extra mode, which is canonically conjugate to this delta U, which I'm calling lambda here. What this lambda is that it's essentially, maybe I should just draw it here. So there is this x1, x2 plane in gravity. And then there is a y coordinate. The y direction is positive. So this is y. This is the y direction. Asymptotic AdS, by the way, lives at y equals infinity, and this is the x1, x2 plane. Now, in the present, so when you have a four-form gauge field, it can have a holonomy or a Wilson line from this point x1 and x2 up to asymptotic infinity. This is just a Wilson line. In other words, take A4, the four-form gauge field, and integrate it outwards. It's a four-form, so you also have to integrate it on one of these three spheres. So there are some subtleties that I'm not going through the details of. But essentially, the point is that there is this holonomy from the plane at y equals 0 and y equals, between y equals 0 and y equals infinity. And that is the mode, that is what I'm calling lambda. Okay. So there's this new mode associated with this holonomy, which sort of enters this symplectic form. Now, the interesting thing here is that if you had done this calculation around a microstate, by which I mean a state where U is either 0 or 1, then what you would have found is that this holonomy or this extra mode lambda just drops out of the symplectic. Okay, the reason that happens is that in microstates, as you go to y equals 0, the geometry is completely regular. So either one or the other three spheres shrink smoothly to 0, and there is no boundary. So this holonomy that I'm talking about is a pure gauge mode. Okay. However, in the presence of this black hole, what happens is that this x1, x2 plane is not regular anymore. Okay. So in other words, you should really think of this geometry is sort of living on some stretched horizon outside the black hole. And then, because you have a stretched horizon, this holonomy sort of becomes like a physical mode, and that enters the symplectic form. Okay? So that's the sort of picture I was trying to indicate here. You have this microstate, which is highly quantum, has no classical description, but you can think of the black hole as sort of being a coarse-grained description outside some stretched horizon. And then the holonomy is sort of this pure gauge, this mode, which would have been pure gauge if I went all the way down to the quantum scale, but up here, it's a physical degree of freedom. And that's what enters this gravitational symplectic form. All right, so.
Am I supposed to take literally so you're freely switching between position and momentum space, right? You have PQ and you have X1, X2?
Oh, X1, X2 are just Q and they're the same.
Okay, but X1, X2 are actually physical coordinates.
That's right.
Geometry.
That's right.
So I'm really supposed to take literally this.
It's literally, yeah.
So that picture is literally on the surface of the black hole.
That's right. That's right. That's right. So that's how this correspondence works. The X1, X2 space-time coordinates in gravity are like P and Q in quantum mechanics.
But you're going to have some kind of like collection of rays of these lines coming out. Is that right?
That's right. That's right, and that's the speed of lambda. All right, so I have like maybe 2 minutes left.
Yeah, so for the phase space, I normally have some flexomorphisms, right? When I think about canonical transformation from the phase space, when it comes from this tells me what is P and what is Q. But here, I mean, on X1 and X0, I have diffeomorphisms, right? So which are in some sense larger. So how can I see that I really can make this identification?
Well, so one way to see that is that if you take so for example, if you go, so the way Maoz and Richkoff would say this is that if you do this calculation in a microstate, what would happen is that the symplectic form of 2D supergravity reduces to something, it reduces to a sort of symplectic form on this Q and P space. And it ends up being the same as the sort of symplectic form that you would write down for this free fermion theory.
Yeah, no worries, sorry, I do not want to interrupt you. It's just a little bit confusing, you know, how you see that these coordinates, as William was saying, I mean, really in target space, which is configuration space.
Mm-hmm.
But you say you have a phase space, but then you also have a configuration space, but then you take one configuration space coordinates and say it's a phase space coordinate.
Yeah.
So it's just saying that this particular thing happens to be symplectic. There's also it's symplectic in the field space, right? It's not actually saying that X1, X2 is
It's also, so it's both. X1, X2 is also a symplectic manifold. It's the phase space of a harmonic oscillator.
Yeah.
But here I'm talking about the phase space of these sort of black hole excitations. That's slightly different. I agree.
Yes, the density fluctuations in your disk are paired, have canonical conjugates that can be interpreted as Wilson bonds for each one.
That's right. That's right. So that's at least that's what gravity does. And so really the main thing for us is this was a little bit of a mysterious result because this mode. So the basic question for us was how to interpret this mode lambda from a CFT perspective. Where is this mode lambda in the CFT, or how do I think of it in the CFT? Because this lambda is really like a soft mode. It doesn't have a lot of energy. Like it sort of at leading order in n, it drops out of the Hamiltonian. Okay, because in some sense it's a pure gauge mode being associated with this holonomy. So really the question for us is whether we can think of this mode lambda from a CFT perspective and relate it with some kind of a microstate, a mode associated with microstate deformation of the black hole. All right, so do I have a few more minutes? Like it's 3:42 right now.
Yeah, sure.
Okay,
It's
so
amazingly on time.
So let me just very, very quickly tell you how to think of this mode in terms of the CFT. So the idea is, from a CFT perspective, you can thinking about these geometries from a CFT perspective basically means going back to these microstates. Okay. So in gravity, we sort of coarse-grained and looked at the black hole geometry. But now let's go back to this microstate. Okay. In fact, what we'll do is we'll go back to this picture, to the microscopic picture, and let's look at some region of it. Let's just look at this. Zoom in onto some region like this. Okay, because we are interested in local fluctuations of the black hole. Let's zoom into a region like that, where the picture is just like you have some rings. Okay. And so on. So I'm just zooming into a region of this microstate. Now, if I want to deform this, there are a few things I can do. First of all, if I want to construct a grayscale fluctuation like this, or a fluctuation of the geometry like this, one thing I could do is I could sort of pattern these rings in some way. So hopefully you can sort of see that if I do that, what's going to happen is that in the coarse-grained description, the grayscale, what looked like a gray blob or a gray disk, is going to, because of these sort of fattenings of these rings, is going to have a small increase in its grayscale. So this is going to look like some grayscale fluctuation from a macroscopic point of view. So let me call this the A mode. But there's another thing I can do, which is that I can sort of translate these things. Okay? This is a different fluctuation from microscopically. Just sort of a uniform translation in some local region. But when you coarse grain, or in other words, when you zoom out of this region, this fluctuation is not going to increase or decrease the grayscale. Okay? From a coarse grain perspective, this is going to look as if you're in the original undeformed background, or undeformed grayscale. So let me call this mode delta P. Okay? So now in the CFT, there's a well-defined procedure to calculate the symplectic form for fluctuations like these. Okay? I'm not telling you the details here for a short bit of time. But basically what you do is you compute some kind of Berry curvature. Okay? It's quantum mechanics in the CFT. So to extract a symplectic form, the way to do that is you calculate a Berry curvature. And when you do that calculation, you find that the symplectic form again becomes of this nature, but you find that these A and B modes are coupled together, okay, in the CFT. In fact, what this A mode is it's precisely the analog of this delta U. It gives rise to grayscale fluctuations from a coarse grain point of view. And so if you compare between the gravity and field theory results, what that's telling you is that what we thought of as the soft mode in gravity is one of these deformations, which from a microscopic point of view is a completely well-defined deformation, but I guess the way to say that is that it's a well-defined IR deformation, but it's embedded in the UV of the Hilbert space, in the sense that it's really a microstate deformation. When you coarse grain or you zoom out of this region, you're not going to see this delta B in terms of the grayscale density or as a fluctuation of the metric, but it does interestingly show up it's not entirely absent from gravity. the way it shows up in gravity is in the form of the soft mode as a holonomy between the horizon and the asymptotic infinity. Okay, so that was the main gist of what I wanted to say. So just to summarize, we described sort of the phase space of fluctuations around a specific black hole, one whose microstates we understand very well. In the gravity calculation, we found this interesting soft mode, and because we understand the microstates of this black hole very well, we were able to give a microscopic interpretation for what this soft mode corresponds to in terms of deformations which sort of mix you within the microstates of the black hole. And in future work, we are trying to understand whether we can use this soft mode to compute the entropy. So there's a nice formula for the entropy of this black hole. In terms of the area, essentially the entropy of this black hole is log 2 times the area of this gray disk. Okay? And so our hope is that we can understand that entropy from the perspective of this soft mode. So I'll stop there. Thank you. Yeah.
So this was a specific example. Like, does this relation between soft modes of both CFT and black hole side generalize to other cases?
Which so